experiment 3, chromatography, is our first not identification technique, but separation technique. Now, that being said, you absolutely can use chromatography to identify something by running a known compound along with an unknown compound, an unknown mixture, and separating it and then matching across to see if one of your spots, if you're doing thin layer chromatography, matches a known compound. But again, it's a data point. It's not absolute, unequivocal identification. But very, very, very common in organic chemistry to run a thin layer chromatography of your starting material and then run a thin layer chromatography at the same time, right next to it, of your finished product, and see if your starting material has disappeared and if your product has appeared, or if a new thing has appeared, so that you can attribute it to your product. So the first two labs were all about collecting data points, physical properties of compounds in an effort to identify them. In this lab, we have mixtures of pure compounds, so multiple pure things mixed together, and we're trying to separate them. And we will separate a ink pen, a black ink pen, which is going to be composed of a variety of colors, and that's what makes it black, absorbing all light, using thin layer chromatography, and we'll separate a mixture of liquids using something called column chromatography. So we'll go in order, I think, this time, but you could do step 2 before, or part 2 before part 1. So for thin layer chromatography, we have our mobile phase, which is here, hexane ethyl acetate, and that is going to be our mobile phase. The chromatography technique always has 2 phases, as was mentioned in the introductory video. A stationary phase, which is on this piece of plastic. This is silica or alumina stuck to the plastic. Now, back in the old days, they'd give you a sheet of glass, which you had to cut into little rectangles like this, and then they would give you some powder, and you would mix it with some of your mobile phase in a beaker and kind of swirl it up and dip your glass in there, not cutting your fingers, and hopefully you'd end up with a thin sheet of your stationary phase stuck to the glass. Now, we make life easy for you. They give you this plastic thing with, hopefully you can't cut yourself on, with the stationary phase already stuck to it. And we'll put our unknown, our ink pen, at one end, and this mobile phase will move across the plate with capillary action, and hopefully we'll get some separation as we go along. So it says, put about 1/4 of an inch, 5 milliliters or so, of the mobile phase into this developing chamber. Now, this is very fancy. Again, back in the old days, you just get a beaker and a lid or something to cover the top of it. And this is actually made for TLC. It's got little slots in there, so that theoretically you could run multiple plates at once by carefully standing them up in there. Right? We could have multiple of them. We're just going to run one at a time. So, 1/4 inch of our mobile phase, again, cap up, a little bit of our mobile phase in the bottom of here. Okay, not too much, but enough where it runs up the plate. We're not going to have it completely dry. And we want to keep this covered so that as it evaporates, it just evaporates into the chamber. We want the chamber as saturated with the mobile phase as possible. So just a few millimeters deep, and we covered the chamber immediately. We're going to get our TLC plate, which we've got. We're holding it by the sides, so we don't want to get our greasy fingers all over it. But if you're wearing gloves, I suppose you could touch the top of it. There's a shiny side that is just plastic. You don't want that side. And then there's this side that has the powder stuck to it. It's a very thin sheet of powder, so if you scrape it hard enough, I'll just do it with my finger here. Not so easy, all right? Do it with these scissors here. I mean, you can definitely scrape the powder off. And you don't want to do that because breaks in the powder make for a bad TLC. Right? So don't trash that. Get a new one. All right. So I have my TLC plate, and we're holding it from the sides just because we don't want to have any markings on it. And we're going to put it on a piece of paper towel, I suppose, if we want to. But I think right on the bench is probably good enough. It's easier to pick up if it's on a paper towel. And we're going to draw a straight line along the bottom. Now, we don't want to scrape the heck out of the plate with this pencil, because we'll just destroy the powder. And if you have a break in the powder, then the liquid won't be able, right? This is going to be in the chamber. The liquid's going to be pulled up by capillary action up the plate, and if I have a break in the powder, the liquid just would stop. I don't want that. I'm going to carefully draw a line, hopefully nice and straight, hopefully nice and even. 1/4 inch to a 1/2 inch from the bottom. Very light, right? So I have my line. This is my plate. Okay? Now, that's my starting point. And you'll notice, okay, when I hold it right there next to this, it's definitely going to be above the liquid in the chamber, which is good. If I start with my mixture that I'm trying to separate down in the liquid, it's just going to go into the liquid, and it's not going to go, the liquid as it comes up the plate is not going to pull the sample with it. It's just going to dissolve into the liquid at the bottom. So we don't want that. All right, now my mixture that I'm trying to separate for this lab is a ink pen. It could be some liquid that I have produced in an experiment, but we're just going to separate this ink pen. So nice fine tipped marker, and I'm going to put a little dot on my starting line. Okay? Very small dot. I'll show you what happens if I put a bigger dot next to it. So I'm going to put a big dot here. I'm just going to hold it on there. Put a big honking spot. I'll do it a couple times. Dot, 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 dot. Okay? And we'll see which one works better. Right? Got my big honking spot, and I got my little dot next to it. Okay? Carefully into the chamber. Now if you look closely, you'll see that the liquid is definitely below the spot. Okay. Really shouldn't disturb this. I'm being very careful as I put it down. Get my chamber covered. Sometimes you can put a piece of paper, filter paper, in the chamber to help keep the chamber saturated with vapors. Just don't see any filter paper in my supplies here, so I can't do that. And now we wait. Patience. We wait. As the capillary action pulls our mixture up the plate. We have it undisturbed. Solvent is rising up to the spot. Unfortunately, our spots are kind of going towards each other, which is a little bit whack, but so be it. Hopefully they'll straighten up and they won't collide with each other. That's why I put them on opposite sides of the plate. And we're just waiting for that solvent to get as high up as we can, but we can't let it go all the way to the top. If it goes to the top, then our spots are going to keep moving also, and just going to recombine. We don't want that. The goal here is perfect separation. Our large spot on this side is just a big mess. Our small spot is a little bit better, but not a whole heck of a lot better. But our solvent is only here. Our mobile phase is only there. We gotta wait for it to get up a little bit higher. Notice the solvent is definitely below our starting line, which is what we wanted. There's effectively nothing left here where we started. A little bit maybe here, but it's hard to say. But sometimes you will have something remaining where you started. It just means that your mobile phase really didn't interact with it, and so it just stayed there. Our mobile phase seems to be interacting with our ink and separating it into there. It looks like there's a blue spot, and then maybe a purple spot, and a red spot. Looks like that's still black, and then there's another orange up there. We're definitely getting some separation, and as we let the solvent move farther, hopefully we'll get some actual space between these colors, which is what we need. The dark spot, you can see, just a mess. So that's why it's very important when you do TLC, thin layer chromatography, TLC, that you don't put too heavy a spot, or you just end up with a mess. Even my very, very light spot, these guys are still kind of streaky. Hopefully, as the solvent moves up, we'll get a little bit better separation. Still waiting. Not a whole heck of a lot of further movement, but we'll see if we get any more. Alright, I think that's as good as we're going to get movement-wise. Remove the plate. Should put it on a piece of paper towel, but doesn't really matter. Quickly mark where the solvent was. Alright, and then I'm going to mark the center of each spot. There's a really dark blue one. There's a pink one. There's a lighter blue, and even lighter blue, and even lighter blue. I see something else there, and then that's about it. Okay, so I have 1, 2, 3, 4, 5, 6 spots. The really dark one you can see is just a giant mess that's streaked into itself. So that's nothing. I'm not going to use that. But I need to get precise measurements from where I started to where the solvent stopped, and from where I started to where each spot stopped. And I'm measuring to the center of each spot. So I have my handy-dandy ruler, which is marked in centimeters and millimeters. I'm not going to use inches because, you know, we're in the United States, but still. Let's go metric, like science. And use my centimeters and millimeters. So it's going to require some very, very careful measuring. I'm going to put the 0 exactly on my starting line. Let's see if I can show you guys this. Right, my 0 is right where I started, and I'm going to measure to each spot and to my solvent. Now, it's critically important that I note that there are millimeter marks on this ruler, and that means I must guess to the tenths of a millimeter. Is it between 32 millimeters and 33 millimeters? And how far in between? And so on. So that's what I'm going to do. Okay? So I'm going to start with my solvent distance first. Now my solvent went, it looks like, almost 43 millimeters. So I'm going to call that 42.9 millimeters from my starting point, not the bottom of the plate, to where my solvent ended up. My first spot, my blue, dark blue spot, is at 41.9. My red spot, my next one, my red spot, is at, right on the starting point, 38.5. My next spot, my lighter blue spot, is at 37.0. It's right on the line, okay? I don't just write 37 because that means it was between 30 and 40, but closer to 40. It's 37.0 because it's right on the line. My next spot, my lighter blue spot still, is at 35.4. My next spot, which was very light purple, is at 33.2. And finally, my last very, very, very light blue spot is at 30.4. 30.4. Okay? I think you have to put an extra line on the data sheet for all of those different spots. But again, hold it up so you can see. There's definitely all of those different spots there. And I have marked the centers of each of those spots. What you're looking for in thin layer chromatography is something called good resolution. The spots should have white space in between them. And I think if this were better focused, you could see that there is white space in between those spots. We can divide the distance that our spot traveled by the distance that our solvent traveled, our mobile phase, and get what's called a retention factor or retardation factor, RF. And RFs are unique to compounds for this exact experiment. Right? If I did this ink pen with a different solvent, I might get different RF values, but I would get the same RF values if I did it again in the exact same way. If I did a different day, same solvent, different plate, I might get different RFs. But if I repeated it again, I would get the same RFs twice in a row. So that's why you can run, at the beginning of an experiment, you can run a TLC, and then at the end of the experiment, you can run a TLC. And you should get an RF that's the same for what you started with, and then a different RF for what you ended up with. All right, so that is thin layer chromatography. Part 2, column chromatography. Column, so named because it's usually in some sort of vertical container that's narrower than it is long, and so it's a column. This is useful for separating larger amounts of materials. Sometimes this thing could be 30 or 40 feet long and maybe 10 feet across for massively bulk separations. The thin layer chromatography, that's pretty much the size that it usually is. And you can only separate, just very, very, very small dots of stuff. You can try, just while I'm thinking of it, thin layer chromatography at home. It works with a paper towel and water as your mobile phase. So you could just take your paper towel and have a beaker or a cup, even a coffee cup, and take your paper towel, put some ink on your paper towel at the end, and then just dip the tip of it into your cup of water, and the water will rise up the paper towel with capillary action and separate your ink pen. So you can try this at home just with water and ink. But column chromatography is a little more involved. We need to have our stationary phase, which is a white powder you can see that you should not inhale. This is alumina. Sometimes it is silica gel. Both can cause mesothelioma from inhalation, so you want to protect yourself from that and not get it in your lungs. But that powder is so fine it would just come out the tip of this pipette. So we need to clog up the tip so that liquid can come out, but not the solid. So I'm just going to use a cotton ball and take a little piece of cotton, little piece of cotton, and I'm going to poke it with this paper clip and straighten down. Poke it with this paper clip down into the bottom. Now I don't want to do this too tightly, because then the liquid won't be able to go through. All right? So it's there, and now my alumina won't come out the bottom. I'm going to clamp my column into a burette clamp. Now this clamp is pretty strong, and so if you do this not carefully, you will snap your pipette right to pieces. So it's clamped in there. Okay. Now I need to get my powder into there. How can we do this? Ingenuity. I'm going to put some powder onto this piece of weighing paper, which is just wax paper. Not going to take too much. Again, cap up like always. And now very carefully, I've folded my paper in advance, I'm going to put some into this column. Now I can't fill it all the way up, because if I do that I won't have any room to add my liquid. That's enough. I've still got a good inch or so of space. Now I did take too much powder, and I have spilled it all over the benchtop. I'll clean that up later. but I'm going to put this in a proper waste disposal area. Okay. Chemistry can be a little messy. We'll clean this up later. I'm not, absolutely not, going to scrape this into the sink though. That would be bad. Okay, so I have clamped it to the ring stand. I have used my burette clamp very carefully. I could use a different kind of clamp and kind of wrap this thing with paper towel, but this works just fine. Now, I need to put some test tubes under here to catch my solvent as it drips out. So I have a test tube rack with test tubes. Now, our compounds that we're going to separate are colored, so they're very easy to determine when one compound has left the mixture and the other one has remained in the column. But a lot of times, especially in the organic lab, the mixture that you're trying to separate is completely colorless. It just looks like a clear, colorless liquid. And so what you do is maybe every 5 milliliters you switch from this test tube, 5 more milliliters, switch to this test tube, 5 more milliliters, switch to this test tube, 5 more milliliters, switch to this test tube, etc. Because you're collecting fractions, they're called, as they come out, because you don't know what's in a column, in a fraction or not, because you can't see it. So you just run TLC on each fraction and look at where the spot is, maybe with UV light or something that will make it, or iodine to make it become visible. But we know that we have a mixture of 2 compounds that are colored. So what I'm going to do, according to my instructions, is I'm going to fill the pipette with the first solvent, and it says that I should use water as my first solvent. Now, I could use, instead of deionized water, it says distilled on it, but it's deionized. We don't have a distiller here. I could use my drinking alcohol, my ethanol, which the label has worn off, but it says ethanol on there really, really lightly. I could use the ethanol first. It's just that the order of my compounds coming out would be switched up, and my unknown, there's a few things that I know about it. Number one, I have written on the side, it says dye for column chromatography. I know it has 2 components. I know what they are, and I know that the liquid that they are dissolved in is in fact water. So if I used the ethanol first, my order of my things coming out would be different, and also this is in water, so the first couple of drops might be not fully separated. So I'm going to fill my column with water. Now there wasn't much that room in there, so I have to keep adding it. It's very important in column chromatography. Put my test tube rack right underneath it. Lower it down even so that the tip is right in the test tube, so I don't spill it all over the bench. It's very important in column chromatography that the stationary phase, the solid, is always covered with liquid. Now that's not so much of an issue here because this column, gravity pulling the liquid down, doesn't really work that well. And so we do a technique called flash chromatography, where I take a pipette, see how far it would go into one of these glass pipettes. Right? So it can go in about that far. I'm going to cut the tip off of this plastic pipette and use it as an air blower to blow my mobile phase through, just to speed things up. Okay, so I have my air blower here, and I squeeze the air in. It blows the liquid in a little bit. And I take it off, let it refill with air, put it back on tight. Careful, hanging onto that. Squeeze it through. Otherwise, we'll be here waiting forever. Squeeze it through. Now you can see, I can pull it back down, but there has been a drip coming through. That's what we want. Good. Again, squeeze some air in, try and push this stuff through. Once my mobile phase is almost exactly on top of my stationary phase, that's when I'm going to add my mixture that I'm trying to separate. Now I don't want to add it when my liquid is all the way up here, because then it's just going to dissolve in the mobile phase. I want it right on top of the stationary phase. Yep, made a bubble in there. Need to pop that bubble. Go back to my coat hanger. Paper clip. Drop number 1 is on, but we still have a little bubble there. Very annoying. Get a second drop. Okay. The mixture is on. You can see green on top. I seem to have yellow and blue there. Funny how that works. Yellow and blue makes green. So I'm waiting for my mixture to hit the top of the stationary phase, which it pretty much has. So now, again, I don't want to add this water prematurely because it'll just dissolve my mixture in it and not carry it through the stationary phase, which is the goal. Again, I'm going to use my air pump here, attach it on really tight, blow, but not let it blow out, hopefully. For bigger columns, they have special glassware that attaches to the top of the column to blow the air through. We're not that fancy in the introductory general chemistry lab. I'm getting some drips coming out, so I have a good phase. The key is to make sure that I keep this squeezed until I take it off and then let it refill. If I let go of it while it's still on here, it'll suck the stuff up, which we don't want. And squeeze it through. Take it off, let it refill with air, squeeze it through. Again, my solvent has hit the top of my stationary phase, and so I'm going to refill. But what I really, really want you to notice here is I have, close up, blue component of the mixture, yellow component of the mixture, still coming out colorless because the yellow part hasn't gotten there yet. So I could throw away this first fraction, but I don't need to. I know it's just water solvent. I'm going to wait and keep adding water until all of this yellow has come out. Now what if I didn't know what solvent to use? That's the artistry of chromatography, where I have to try a solvent, and then based on its physical properties, if it doesn't work, try a different solvent based on its physical properties. Usually we look at polarity, which is something that we'll get to later in the semester. But water seems to be the right solvent for getting this yellow out, but leaving the blue, which is perfect because I get my separation that I was going for. Right? My water level is still well above the top of the stationary phase. So, unless I want to wait here forever, I'm going to blow that through with some air. Here we go. Blow it through. Much faster. And you can see the yellow is definitely now dripping out into the test tube. Speed things along here. My mobile phase is now right at the top of my stationary phase. I'm going to refill with water. How do I know when to stop refilling with water and switching solvents? When I have gotten all of that yellow component out. What if it was something that was colorless? I would be running TLC and developing my TLC plate with iodine or under UV light and seeing what was going on. But this stuff that's coming out right now, this bright yellow, is actually glowing because it is fluorescein. Stuff, if you're the optometrist, they add to your eyes so that they can see your eyeball better at the doctor's office. But I definitely still have yellow coming out. Get close up. So I'm going to keep blowing air through. And keep blowing it. And keep. And keep. At my stationary phase again, so I refill with my mobile phase. Still looks a little yellow coming out. That, I think, is pretty colorless. We can switch test tubes to see and be sure. It might have still been a little yellow, but let's try it right now. Notice this test tube, nuclear yellow, like something right out of The Simpsons. Switch test tubes. Just confirm that this is coming through now totally colorless, so that we're done with our first component. Let's find out. I'm going to blow it through so I get some quick drips. It was very, very slightly yellow, that first drip, but the last drips that are coming through now are definitely nice and colorless. So we're ready to switch to our second solvent because we still have a component of our mixture stuck to our stationary phase, our second component of our mixture. It was not at all attracted to the water. I mean, it was attracted enough where it was dissolved in it, I suppose, when it was in the bottle. But I kind of shook the bottle before I put it in there just to be safe. So this is not really being drawn through. Also, it's competition. It may have dissolved in the water, so it was attracted to the water, but this blue component of our mixture is more attracted to the alumina than it is to the water. All chromatography is about competition. My component's attraction for the stationary phase versus its attraction for the mobile phase. And the yellow component was attracted to the stationary phase not nearly as much as it was attracted to the mobile phase of water. But the blue component was more attracted to the stationary phase than the mobile phase component when it was water. So I need to switch mobile phase components. So I'm going to switch to ethanol. Why? It's less polar, but we haven't gotten to that in class, so just trust me. That's what we're going to do, is go for the ethanol. All right? So let's do that. Instead of water, we don't need that anymore, we'll switch to refilling our column, which still is covered with water. We're going to add ethanol on top of that. And let's keep an eye on that blue as I blow this through. You see it? Refill with air. Blow again. And again. And again. And again. And again. Keep doing this. Flash chromatography because we don't feel like waiting around for gravity. My solvent is too low, right at the tip of the stationary phase, so I'm going to refill. Get it close up here. Notice where the blue is. It's not just at the top. It's moving down. So we have some attraction, that blue component of our mixture, for ethanol. The two components of the mixture, if you care, are fluorescein and methylene blue. Methylene blue is more attracted to ethanol than it is to alumina. So we can blow that blue component through. Want to make sure that the solvent always covers the stationary phase, because if it doesn't, You get little cracks in the alumina, and then it's just like having a break in your TLC plate. You don't get good movement of your components of your mixture. And my blue has not yet quite hit the bottom. Actually, it has hit the bottom, so I'm going to switch test tubes again. That was our slightly drip or two of yellow. And now we're going to go back to careful, I don't break that. Let's see if we see our methylene blue. Refill, because my solvent was going to drop below the level of my stationary phase. Again, refill with ethanol. Ethanol is drinking alcohol, but you never want to drink alcohol in the lab because a lot of times it's been distilled with benzene and there's a touch of benzene left over. Most labs these days do actually have 100% ethanol. If you want, this would not be 100% ethanol because it's just made for washing. But still, don't drink stuff in the lab. Bad idea. Now you can see, there's very, very little blue left at the top, some residual. There is, interestingly, some blue in the cotton. Our methylene blue seems to be very attracted to cotton, but in our test tube, hard to see in the blue rack, let's see, methylene blue in ethanol. So we could take this ethanol and evaporate it and end up with our methylene blue, which is relatively expensive. If we wanted to get it back, we could take our water and carefully remove it and get our fluorescein back. And so we will have separated our mixture into its two individual pure components using the separatory technique known as chromatography. And then, for safety purposes, we would very, very carefully clean up our alumina, put our liquids into their proper waste containers, and put all of our equipment back where we got it.